So in my trade, as I look out at the audience gathered here, we would call that a critical mass of news reporters. So we'll see whether the critical mass goes off or not. I've also heard my name mentioned so many times last night and this morning that I'm almost tempted just to say, look, I have prepared a presentation. I'm almost tempted to put it aside and say, are there any questions?
We can also do that.
I have a question. Could you be louder?
Could I be louder? Okay, let's see if, can you do it electronically or do I have to speak up? Okay. The electronic is for the recording. Could I be louder? I usually ask that because I tell my students that my hearing is electronically assisted. You know, that's how you start to say things as you get into the older generation. So the other thing that really strikes me here, again, as I look out at the atomic reporters, quite frankly, it is, I hope you don't take this the wrong way, but this looks more like one of my classes than the other places that I lecture. So I'm immensely impressed by the youth that I see in here. And to sort of second Eric's comment, you know, that's really the hope for all of us. Okay, I don't see a whole bunch of hands up, so you're going to have to suffer going through this with me. I was asked to give an overview, and quite frankly, I don't quite know what to do with an overview of a subject like nuclear weapons. And so what I thought I would do is first to show you maybe 10 or 11 PowerPoints of the hardware of nuclear weapons. And then the most interesting aspect of what I'd like to present and actually discuss with you is more of the software aspects of nuclear weapons, because that's really where I've spent a lot of my last 30 years. So just, again, and I'll go through this quickly because you can find this in textbooks, but what I found in teaching, and I've taught, at Stanford, I've taught over 3,000 students at a very popular class, average 255 students a year for like 12 years. Then I had a small class. And that interaction was so fantastic for me because it really taught me as to how do you try to approach these subjects. And so let me just sort of walk through this. So there are three main characteristics of things nuclear that are really important. So one is they're just that much more energetic. And that's what nuclear is about. So when you split the nucleus, or if you fuse the nuclei in fusion, you're talking about hundreds of millions of times the energy released in almost all other normal things, which are controlled by electrons. And so whether you burn coal, whether you burn oil, whether you do anything, those are electrons you're dealing with. The energies are electron volts. When you split the nucleus, you're talking about sort of 100 millions of electron volts. And that's what you have to keep in mind. And so even though you don't like things nuclear, particularly the bad things that come with nuclear, it's there. That energy is there. So first of all, it's that much more. And this is what happens when you split a nucleus. As you can see on the left, the nucleated fission, I'll tell you a little bit more about that, but uranium-235, the isotope 235 uranium, when you split it, it splits up and it gives you that sort of energy. And so these fission reactions, the second thing, they're sort of 10,000 times faster than normal reactions in electrons. And so that, you know, as you can tell here, that's really, really important when it goes that fast. And then third is that you can get a chain reaction. So you split one of these nuclei, that liberates more neutrons. The neutrons then split more, and so you get a chain reaction. You put those three things together, and in essence, you have an atomic bomb as a possibility. So that's just one fundamental thing. The second one is that it's basically the heavy elements that can fission. And here's a periodic table. I show Dmitry Mendeleev. And so even though today, and as Eric Schlosser said, those Russians are really bad guys, but not all Russians are bad guys. And if you go back in history, the scientific history of the Russians and Russian nuclear is just absolutely amazing. Mendeleev in the late 1800s is the guy who put together the elements in a fashion that you can actually try to figure out as to why are they similar. Of course, Mendeleev didn't know about these actinides yet. They came later with, for example, with Glenn Seaborg actually made the first man-made plutonium out of Berkeley in 1941. But it's these actinides, and then particularly the two elements that are practical for fissioning are uranium and plutonium. And it matters what isotope it is. An isotope is the combination of both the number of protons, which has to be the same as the number of electrons, and the number of neutrons. In neutrons, you can stick in a lot more neutrons. So that's why you have uranium-235. That's the stuff that we eventually call highly enriched uranium if it's over 20% of that in the uranium. It turns out, essentially, nobody talks about it. Uranium-233 also fissions. And actually, uranium-233 is made if you can make thorium actually pick up a neutron. And so a lot of people talk about thorium reactors, and they would be better because they don't make plutonium. Well, it turns out thorium reactors make uranium-233, and you could make a weapon out of uranium-233. So you have the two uranium isotopes, and then you have plutonium-239, which is the isotope for nuclear weapons. Okay, this is the diagram, so the cartoon that I use in class to show, look, there are basically two types of nuclear weapons, that is fission weapons. And one is uranium-235, and that was Hiroshima. And that's a very simple technique. You take two subcritical masses of uranium-235 and you fire them at each other. And you can do that in a gun barrel. And if you use HEU, highly enriched uranium, that is typically at 80 to 90% uranium-235, then you can get the atomic bomb, and that was Hiroshima. Now, what Mother Nature gives you, these fissile materials you can't just dig up out in the ground. What Mother Nature gives you is uranium that is mostly uranium-238. And that is because it decays so much slower than uranium-235 than it was all produced, back in the Big Bang area. Today, there isn't much 235 left in nature. And so what you have to do is then essentially enrich the uranium. And so that's what you've heard when you hear about enrichments, when you hear about centrifuges. What enrichment means, you throw away the 238 and you concentrate the 235. And if you get it up to 80 to 90%, then you have weapon-grade uranium. And that's, in essence, what was done here at headquartered, let's say, at Los Alamos in terms of the atomic bomb design. The enrichment was done at Oak Ridge. And it takes, let's just say, some tens of kilograms of highly enriched uranium to make a bomb. Actually, Hiroshima was over 60 kilograms of highly enriched uranium. And then the scientists up at Los Alamos found out in late 1944 that design isn't gonna work for plutonium. It doesn't assemble it fast enough. And so they then went into this incredible effort in a number of months that they switched from that design, the simple design, to something much, much more difficult technologically. And that is to put plutonium at the center and then imploded really, really quickly with high explosive. And so this is called the implosion design. So plutonium works for that. Highly enriched uranium also works in that mode. And you can make a much smaller bomb this way. And that, in the end, that was Nagasaki. And so now, again, plutonium-239, you can't just go pick it out in nature. Actually, it does turn out there is some plutonium in nature, and that is the 244 isotope. Just decays much, much, much slower. Its half-life is much longer. And so there are actually a few atoms floating around in the world. But for the 239, you have to make it. And the way that you make it today is in a reactor. And the way the reactor works is you put in 238 uranium fuel, and when that picks up a neutron, that becomes your plutonium-239, and that's very efficient. So it takes less than 10 kilograms, and Nagasaki was on the order of 6 kilograms of plutonium. Now, since plutonium, the density, because it's down at the periodic table near the end, is very, very high. It can be between, let's say, 16 and 20 grams per cubic centimeter, so sort of twice that of lead. So 6 kilograms is this. It's a grapefruit. So that's what was in the Nagasaki bomb. And so if you think about things like verification, if you think about a nuclear weapon-free world, think about trying to make a nuclear weapon or a plutonium-free world or a highly enriched uranium-free world. This is really, really difficult because it was one grapefruit, one city destroyed. And so those were the two in Japan. And then the development of the hydrogen bomb, and they figured this out. Actually, Edward Teller, when he was up at Los Alamos, he pretty much refused to work on anything except what he called the super. And the super was a hydrogen bomb because Teller and others had it figured out that if you actually can make atoms fuse together instead of splitting them, then you can make enormous amount of energy. And essentially, the yield or the explosive capacity of a hydrogen bomb is unlimited, whereas a fission bomb is indeed limited because you put so much of that material together, it eventually would fission by itself. And the United States, led by the team up at Los Alamos, developed the first fusion bomb as such, and it was due to a concept that was developed by Edward Teller and Stanislav Ulam. He's actually a Polish mathematician that was up at Los Alamos. And they developed the concept that the way to make a fusion bomb work is you take a fission bomb, like the one at Nagasaki, and you blow it up, and you contain the energy of that fission bomb in sort of a bottle or a case, and then you're able to fuse. And to fuse, you have to take the light elements. And in fact, the light element that you can fuse is hydrogen and its isotopes. And you've heard deuterium, tritium, so that's hydrogen with no neutrons, deuterium with a neutron, and then tritium. So, and indeed, when they blew this up out in the Marshall Islands, it was enormous. So this one was 10 megatons instead of the 15 or so kilotons at Hiroshima and the 21 kilotons at Nagasaki. So this was enormous, but weaponizing it was a whole different story. But this is also something that the Russians, who had these superb scientists, I mean, actually, if you take a scientist at Los Alamos, of course, more than half of them, the scientists, came from Europe and came to Los Alamos. Many of those because of Hitler. And our scientists, both the American scientists like Oppenheimer, the ones that came from Europe, and the ones in Russia, they all went to school at the great European schools of physics. And so the Russians basically had all the capabilities that we did, and they were able to figure this out. Okay, let's turn from the specifics of sort of the physics more into nuclear weapons. And this is what I like to use to try to explain nuclear weapons. And essentially there are three requisites to nuclear weapons, as I indicate here. So first you have to get the bomb fuel, and that's what I was talking about. So you're talking about plutonium or highly enriched uranium. You mine uranium in the ground, and we heard last night, that mining, a lot of that was done here in New Mexico. And by the way, that is the dirtiest part of the whole nuclear cycle, is the mining part, and particularly early on, when we did mining in such, I mean, I didn't do it, but mining was done in such a way that it was really dirty. I mean, like the old coal mining days. Today, the mining is a much, much cleaner operation of uranium than it was back in the 1940s, 50s, and 60s. But, So you mine the uranium, then you either build a reactor and you make plutonium, or you enrich with centrifuges, is essentially the best technique today. So you have to make the bomb grade material. And then you have to weaponize. And you do all of these things here. You have to understand physics. You need computers, detonators, in order to make this thing be able to implode. And you do cold tests of explosives, with simulants for the nuclear part. And then you do nuclear tests. And so that's how you learn something about weaponization, how you're able to make them smaller, make them more powerful, and so forth. And then, of course, you have to deliver them. In Nagasaki, Hiroshima, that was a plane. There's still some airdrop system. I'll show you that later. But today, for the most part, so we're sort of talking about missiles. And then to put all this together, you need command and control. And you just heard from Mr. Command and Control, Eric Schlosser, as to what's there in the challenge of now dealing with these things that you've put together. Okay, so in terms of, how did the nuclear designs advance over the years? Early on, so in the 40s, there were rather few advances. It was mostly trying to figure out how they would be able to use less fissile materials, because it takes a lot of effort to actually make the bomb fuel. However, then from that time on, from sort of 1948 to 1956, there were enormous advances, in nuclear weapons design. And as I show you here, the mass was actually reduced by a factor of 30. I mean, that is really, really immense. And the diameter was reduced by a factor of 3 through nuclear weapons design advances, things like plastic bonded explosives, all of those things, and that allowed sort of a dramatic reduction in weight and size and diversity of nuclear weapons. And so as we look back now, quite frankly, as I look back now, because I've been spending much of my time worrying about places like North Korea and all of the other nuclear countries, as I look back to what was done in the 50s, I must say, I just say, this is crazy. I mean, all the different types of nuclear weapons, including the Davy Crockett Special Atomic Demolition Museum. Can you imagine putting a nuke on the end of this and firing it off?
You're going to see a model of it in the Nuke Museum later today.
That's right. So, and they did. And then artillery shell, to put this thing in a cannon and shoot it out. Or in a backpack. By the way, I had a conversation in North Korea, and it was one time when I'd really set off the vice minister. Usually we got along quite well. We knew how to ask questions, answer questions. But one time I asked him something, he answered, and I said, no, that's really not true. And so he set off and he said, look, we can do anything that you can do. If you can make a nuclear weapon with 5 kilograms, so can we. If you can put one in a backpack, so can we. Well, indeed, they pay attention to what we did. We put one in a backpack. I mean, pretty crazy. But we did. Or a depth charge. If you want to put one. Eric was just talking about what happens to a submarine, in case you have something like a depth charge. So that's what we did. Again, it wasn't me, because I'll tell you in a little while, I got to the lab a little later than that. But this is where we are today, and that is the nuclear triad, the sea, land, and air. And here's the enduring stockpile. Let me actually, if you can get your camera, I'm going to sit down so that I can see this and advance it better. So the triad is here. The ICBM, that's the land-based, all right? So, that's ease of maintenance at remote sites. You have optimized the yield and weight, and you can move independently, go ahead and have multiple reentry vehicles. And so the Air Force calls those reentry vehicles Here's an example that's in the stockpile, the W78, the Minuteman III, and then the W87, which is called the Peacekeeper. And this one has 8, RVs that emerged and has IHE. Those are sort of all the technical terms as to, we also worried about how do you improve the inherent safety of the nuclear weapons. And this stuff is called insensitive high explosive. That isn't going to fire just if, let's say, you drop one of those off a forklift. And then the submarine launch ballistic missiles is the next. There are 2 bases in the U.S. at Kings Bay, Georgia, and Bangor, Washington. The Navy refers these as reentry bodies, RBs. Here's the W76 in a Mark IVA reentry body, and the Trident D5. That's the W88 warhead in that. So that's what we have as the submarine launched ballistic missiles today. We also still have air carry, the third leg of the triad. So these are bombs or cruise missiles. These have been working for years for enhanced surety features. That's the place where Sandia Lab has come in for many, many years. And you heard Eric mention Bob Burafoy. He was sort of one of the all-time heroes of nuclear safety, nuclear weapons safety. Here's the B6111 designed at Los Alamos. We've had many, many variations of that. It's a gravity bomb designed at Los Alamos. The B83 designed at Lawrence Livermore Laboratory. And you can see these things are pretty complex. I mean, there are a huge number of parts that, of course, all have to work together. And here's the case of the W80 cruise missiles. Okay, so that's the end of sort of the quick technical run-through. I don't really do it justice in sort of this quick run-through, but I wanted you at least to have sort of the basics. Those 3 things that it takes for a bomb: the bomb fuel, what the fuels are, where you get them, the weaponization part, and then the delivery part and what we have today. Let me actually just stop here for a minute and see if you have specific questions, because I'm going to get off into this world. This is where we get sort of into the software. A lot of things, the questions that Eric Schlosser asked. Why do we have them? Are we still going to have them? How long are we going to have them? Where do we go? What about other countries that have these nuclear weapons? Yes, please do speak up because of my electronically assisted. Go ahead.
Policy magazine. I'm just curious, given sort of what you mentioned about the physical elements of building a nuclear weapon, that they can be miniaturized much easier. I mean, even from the beginning with Nagasaki, you could make one. You could make a core the size of a grapefruit. Does that sort of make proliferation, over the course of the history of nuclear weapons, has that made it much easier for countries to acquire, build, create a nuclear arsenal?
Well, certainly in terms of the amount of fissile materials that's required. So if you're able to miniaturize, it takes less. But if you look back, even at Nagasaki, it only took 6 kilograms. So from a standpoint of the amount of fissile material there, it wasn't all that different. I should have said more specifically, you can also use highly enriched uranium for an implosion device. And so, for example, if there are countries using highly enriched uranium in their arsenals today, and there are, plutonium is really the premier bomb fuel, but highly enriched uranium works. But certainly, North Korea has highly enriched uranium devices. And you can put those in an implosion device, and it takes a few tens of kilograms. So does it make it easier, for proliferation? Somewhat, but that's really not the big factor. The big factor is certainly the implosion devices are much more versatile, and then in the end, the design is important. The miniaturization is a challenge, and in this book that Valeria held up, of my book on North Korea, I essentially track that all the way through, and I think you might find it interesting. I pretty much explain how the North Koreans sort of went, in the whole distance, And I've done similar things. You know, I've worked with India, Pakistan, and all the other declared nuclear states. Yes?
You know, first of all, Sig, thank you so much for just being here and talking. Now, my question has to do with the aging of plutonium pits. Pits, of course, being the crucial component, critical component on the And as you know, there's this massive effort to expand plutonium pit production. Los Alamos is currently the only production site. You're a plutonium metallurgist. The Jasons came out. Jasons are a consulting scientist. They came out in 2006 saying that pits have serviceable lifetimes of at least a century. They didn't give them an expiration date either. And then, at least in my view, the government and MNSA has not been forthcoming with updated data on pit aging. But since most of your career, a lot of your career has been centered around plutonium metallurgy, I'm asking you, what about pit aging? How long do they last? Why do we need to produce new plutonium pits? Why does the Pentagon say that plutonium pit production is the #1 issue in the modernization of the U.S. nuclear forces?
Well, let's see. We could spend the rest of the time allotted to answer that question, but let me just postpone that for a while. I know you said earlier that that's the question you were really interested in, and I will answer it, but not right now, because I actually have a view graph that at least sort of lays out what the issue and the problem is. So let me wait.
And I'm hoping you could push the boundaries of classification to the extent that you can.
So first of all, I will tell you nothing classified. Okay, so guaranteed. And I have published many things on plutonium and plutonium aging, and we've made those unclassified. And let me just, even though I will talk more about the plutonium challenges later, let me just tell you that 2006-07 report by the Jasons was then revisited in 2019, and they were not, so let's not get into, they were not so sure, anymore. And the bottom line is 100 years for plutonium aging. Let me just tell you, there is no way in the world that you can say that. So that report was wrong, and it's still wrong today, and there's no way that if our arsenal is indeed important to us, if you want it to rot away, and a lot of people think that's actually a better thing to happen, but if you want our arsenal to be there, I certainly don't want to bet on 100 years. Let's see, yes?
I may be presuming something, because you seem very calm and unconcerned, or you seem like a very chill guy. But to the extent that you might be worried about something, what poses a greater security risk or concern when it comes to nuclear weapons? Rogue states, or just an accidental discharge, a miscommunication, a signal misread? What worries you the most?
So that's actually the rest of my presentation. and unfortunately, because what I was asked to do was to give an overview of nuclear weapon, I felt compelled to at least to go through the basics. But to me, that's really not where the interesting stuff is. The interesting stuff is in your question. The interesting stuff is also related to stockpile stewardship and question of plutonium aging. I mean, that's a really interesting, it has an important technical component, but it has much more than that. So actually, let me go on, and then you can come back and you can ask questions. So this is where sort of the software part starts. And what's important, indeed, is that Hiroshima and Nagasaki, as Richard Rhodes said, really made mankind realize its own mortality because of that devastation. And by the Second World War, lots of people were getting killed. And you saw that sort of devastation in Dresden, Germany, and in Tokyo in 1944 and 1945. But what was different about Hiroshima and Nagasaki was this. It wasn't hundreds of planes with thousands of bombs. It was one plane, one bomb, one city gone. That's what nuclear weapons do, and that's why they're so destructive, and that's why it's so important that we know how to manage them. This year is a big year up at Los Alamos because of the film Oppenheimer, which is going to premiere on July 21st. Christopher Nolan. And he's going to talk about Oppenheimer, but this is what Oppenheimer said. After Trinity, and you're going to be down there, the atomic bomb made the prospect of future war unendurable. Because when he saw what was there at Trinity alone, and then of course with Hiroshima and Nagasaki, that was demonstrated. So what I want to do is sort of tell the rest of the story around this diagram, which we in the classified world, we weren't allowed to put this kind of stuff up, some 20 years ago. But then because of many of you and your various requests in the media, eventually during the Obama administration, they actually made this official. And so I just used this because it was the NRDC number. And I said, I don't know if these things are exactly correct, but they sort of have the right idea. So this, and it turned out in the end, it wasn't that far off. And so it's a good diagram to show how the arms race actually developed. And each time I still look at it, I'm still kind of amazed that here in the 1950s and even going to 1962, the Cuban Missile Crisis, look how few weapons the Soviet Union had compared to the United States. And yet it was a crisis that was probably still the crisis of certainly the last 100 years. And you can see the U.S. built its arsenal up very, very quickly, but then it topped out around 1965 or so, and then decreased. The Soviets continued to build up, and whether it was Atoms for Peace here for President Eisenhower, the Nuclear Non-Proliferation Treaty, altogether the numbers continued to go up. And by the way, the U.S. didn't do this because it's benevolence of just saying, oh, we don't need that many nuclear weapons. What the U.S. did was just increase the accuracy of delivery systems. And accuracy is much more important than the actual yield. And so the nuclear firepower of the United States continued to grow the whole time, as did the nuclear firepower of the Soviet Union. So that's the essence. And by the way, even today yet, if you take all of the other weapons in the nuclear world, they're down here. They're very, very close to the bottom. But, 100 nuclear weapons is still a lot of nuclear weapons. Okay. So this is when I came on the scene. Actually, the way I came on the scene, 1956, I came to the United States from Austria. In 1965, almost exactly 58 years ago, I'd finished my undergraduate school, got married, and came to Los Alamos Scientific Laboratory, it was called at that time. Not to build bombs, because it was one of the best 3 scientific laboratories in the whole wide world. That's why I came to Los Alamos. That was in 1965 as a summer student. I worked on plutonium. I'm still here today. I've actually, held plutonium within a week of coming to Los Alamos because I had really knowledgeable mentors. That's when I came on board. And then what I focused on sort of over the next 20 years is here's the plutonium question, Jay. So it turns out plutonium, for its nuclear properties, it's useful for nuclear weapons. But plutonium is actually the most complex element in the periodic table by far, not because of its nuclear structure, but because of its electronic structure. And the electronic structure determines when it melts, it determines how hard it is, whether it breaks easily. It determines sort of all of those other properties that we normally worry about in the real world. And plutonium is the most complex. And I know this is, scientifically might look very complex, but I'll just explain it. Here's the melting point or the temperature as a function as you go across the periodic table. And what this tells you is what's the crystal structure? How are the atoms arranged? And face-centered cubic is a very nice arrangement. So, for example, copper is face-centered cubic, aluminum is face-centered cubic. And when you start in this actinide period, they're face-centered cubic. So they're normal metals. Pretty good. Okay, and here's the melting point. Melting point's pretty high. And then, peculiarly, in the actinides, as you go across, the melting point drops. Essentially, all of the other rows in the periodic table, when you go across, the melting point increases. Here, the melting point drops. So there's something funny about these actinides. And the reasons for that, I've written that in many, many different publications. It's because of the type of electronic structure, what are called the F electrons. And the F electrons are really peculiar. So as you go across, all of a sudden you go from face-centered cubic. It becomes more complex, like tetragonal, orthorhombic. These are all lower symmetry. So you get more and more of these. So they actually change as you increase the temperature. And by the time you get to plutonium, plutonium sits at a knife edge in the behavior of the electrons as you go across this period. Sits at a knife edge. So before plutonium, things are pretty complicated. At plutonium, the melting point is very low. And then as you go beyond plutonium, things become normal again. But everything goes to hell right at plutonium. And that's what I've been studying for 58 years. So the reason I show that, I still don't fully understand plutonium. So even without the aging problem, plutonium is just incredibly complicated. I wrote a paper in 1983 for the 40th anniversary of Los Alamos that was called Plutonium, a physicist's dream, because it does all these great things, so to speak, nuclear, and an engineer's nightmare. Absolute metallurgist, engineer's nightmare. It is a nightmare. To make anything, to cast it, to do anything with it is incredibly complex. And then you add Jay's question on top of that. Now, it ages. Well, you think, aluminum ages, copper ages, the other metals age because they get oxides on the outside. So they oxidize and do that. Well, plutonium gets oxide more than any of those particular metals. In addition, it ages from the inside out because it's constantly bombarding itself through alpha radiation. And so in this crystal structure, you have these, you have these atoms all there, and they're bombarding itself. It's like rolling a bowling ball through this crystal structure, and it does damage. So the good news is in the damage that it does, because of the temperature, we are at room temperature compared to plutonium's melting point, things move around quite easily. And so about 90% of the damage sort of heals itself in plutonium. But 10% doesn't, and that's where the aging comes in. And so we've studied aging. Now, we didn't study aging much. Back in the 60s, 70s, 80s, we studied radiation effects. But we never worried about aging because bombs were supposed to be out there for a dozen years or so. And we knew for a dozen years they're okay. And I was director at the time, as I'll show you here. And I worked on the nuclear weapons program as to how plutonium aging might affect the stockpile, or as to how you cast plutonium and have it be a sound material. And then the program that I worked on, which was probably my favorite, was actually for space power, and that is nuclear batteries. And here again, you use plutonium, but in this case, you use the isotope plutonium-238. And the reason for that, plutonium-238 essentially has alpha radiation that's 300 times what it is in plutonium-239. And what that means, it heats itself much more, which is the good news here, because you want it to heat itself, take the heat, convert it to electricity through thermocouples, and you have a nuclear battery. And so all of these neat pictures you've seen of outer space, from Saturn to Jupiter to Pluto, all of those pictures were made possible by plutonium batteries, plutonium-238. That's the good news. Now, that's where we get into the discussion that we had yesterday about uranium mining. There are a lot of bad stuff associated with uranium mining. There was a lot of benefits to uranium mining. It allowed, for example, nuclear power, and it did allow nuclear weapons and deterrence. You know, how whatever you think of deterrence, but we haven't had a nuclear weapon used for 77 years. And here, the good part was it allows us to do all of these neat things out in outer space, provide the electricity. The bad news is this 238 is really bad stuff. Being 300 times as radioactive. So if you spread that into the atmosphere, you have a real problem. And now we're going to put this together, and you're going to tell me you're going to put this on a rocket, and you're going to shoot this rocket up. You're going to circulate it around the Earth, do a slingshot, and have it on its way out to Saturn. That's a hell of a big risk. We worked on that. So how do you mitigate that risk? That's what we worked on. That's what scientists and engineers do. You try to mitigate the risk. So on one hand, you have this great benefit of all of these neat things. We understand safe, we go investigate. But on the other hand, you have a risk, you have a danger. And managing that risk, that's what I've been trying to do, for the last 30-some years. Okay, so here indeed we have the 20 years that I just mentioned to you. That's essentially, or in addition to finishing my PhD, working at General Motors, worrying about forming aluminum and steel instead of plutonium, and then going back to Los Alamos. So that's what I was doing. I worked in those areas. And then lo and behold, in 1985, it was announced, and I took over as director of Los Alamos in 1986 in January. And to me then, at that point, the world changed dramatically. As I told you, I went to Los Alamos because of the science at Los Alamos. I did my what I thought was my patriotic job. I never went to Vietnam. I got a deferment when I was in graduate school, and I came to Los Alamos to work on these programs.
I think we have about 3 minutes to wrap up, and then all the conversations can be moved to the coffee break.
Okay.
Sorry for that.
Keep going.
All right, that's what happens.
Okay, as you wish, guys. So the audience says keep going.
Okay, I'll try to do this really quick. This is my first year. Jay, where were you in 1986? Yes.
I was in Santa Fe. In fact, my activism was just starting, but your resume is far more impressive.
No, because I had to deal with the likes of you and others. and so I mean, I was 42 years old, all right, and I took over this laboratory. I had a director of public affairs. When we first met, he said, these guys in Santa Fe and these other people, the news media, don't tell them anything. That's what he said. That was my introduction. He lasted 6 months.
Well, I've had my own community relations tell me I'm #1 public enemy.
Well, you're not for me. But at any rate, so I took over January 16th. We had a budget sequestrations like the ones that you've heard in the last few years. The Challenger shuttle blew up. And so now we get, and then we had, FBI came to see me and they say, you have a spy in your nuclear design division. His name is Won Ho Lee. And that's another story for another time. April 26th, Chernobyl blew up. And so you ask me, what am I concerned about? Those are the things I'm concerned about. That technical issues associated with whether it's a rocket. We'd fired those rockets off many times, and yet it blew up. The reactors, which we thought were safe, well, this one blew up. And so here we've got nuclear weapons, and you saw the curve. We got all these nuclear weapons in all of these different places. And so the safety and security of those weapons, particularly at that time, it was mostly the safety that worried me. And this is the diagram that's sort of pretty much guided my life in the last 30 years. And it's what I just said in words a few minutes ago. So nuclear energy, you have this stuff, it can do good. actually deterrence, avoiding global war. If it works, that's good, and we haven't had any. Nuclear.
That's debatable.
I'm sorry?
That's debatable.
No, well, of course. I mean, many of these things are all debatable. And I should have said at the beginning, when I got into the software, that's a very personalized story. And so this is a personalized view that you get from me. And that's why I'm giving you the background. Yeah, I was a scientist. I became director. It's a personal view. That's the way that that's the way I look at the nuclear risks. So there are benefits. Nuclear energy, to me, that's an enormous benefit for mankind. And my students have really begun to appreciate that in the past 10 to 15 years. And then there are medical, industrial applications, these heat sources that I showed you. Those are the benefits. But then there are all these negative aspects. And so again, deterrence can fail. You can have nuclear war, you have proliferation, you have terrorism, you have radiological terrorism, and then you have the health and ecological disasters associated with that whole nuclear cycle. You have all of those things. And so many people just focus on the bottom. And I say, if you just focus on the bottom, you don't get the right answer. You know, when I drive a car, 35,000 or so people are killed in the United States every year when you drive a car. We still drive the cars because we have benefits from driving the car. But of course there, you do it yourself, which is very different than it being done to you. That's what people look at with the nuclear world. But so that's the way I look at the nuclear world. I want to get all the best from the nuclear energy, this factor of millions. And then I want to work on avoiding the worst. And that's where I've spent most of my time. So what is the worst nuclear accident? What's the next worst? And I won't have time to go through this for sure. But let me mention the other book, which was published 2016. It's called Doomed to Cooperate. It's 1,000 pages, sold by the Los Alamos Historical Society. And it talks about what we did together with the Russians after the dissolution of the Soviet Union. So what was I worried about in 1988 when I met with the Russians, actually at our nuclear test site, and then our people went to their nuclear test site, is that this country just came apart. It was coming apart in 1988, and on December 25th of 1991, it came apart. And they had nuclear missiles, bombs, warheads, nuclear materials, people, everything. And so what we worried about, this is what I worried about, is loose nukes, loose nuclear materials, loose nuclear people, and loose exports against so on. That's what I worried about. And that's what I dedicated a good part of the next 20 years of my life to, is to make sure that this wasn't going to explode in our faces or in the Russians' faces or in anybody else, because that was the danger. So to me at that time, it was not how many nuclear weapons do we have? Do we get a nuclear weapons-free world? I said, this stuff is out there. What are we going to do about it? And what we did, we worked with them for 20 years, hand in hand. I've been in Russia 57 times, working with the Russians, and with numbers on the problem. These were the numbers, 40,000 nukes. I told you about 6 kilograms of plutonium or a couple of tens of kilograms of. They had 1.4 million kilograms of this stuff. 1.4 million nuclear people. The brain drain, as President George H.W. Bush called it. 1 million people in their complex, and huge, all everywhere. And so this is the story that's told in the book, and I will try to wind up here quickly. We worked together with them, people at Sandia, people Lawrence Livermore, the other DOE laboratories, and many others that work closely together. But by the way, I also show in the book, actually, I don't have anything against NGOs or the important role that people played in the NGO community during the time of the dissolution of the Soviet Union was just remarkable. And the book isn't about them, but I give them credit for actually moving the government in a direction that allowed us to do many of these things. Okay, the bottom line is, so here we were. This program ended in 2014, actually right after Putin annexed Crimea. And where we were left in the end, because today we can ask the questions, was it worth it? These bad Russians, we helped them. Well, yeah, their nuke didn't explode. there are very few leakages of nuclear materials, very few leakages of people. And then in the end, their export hasn't been that big a problem. They've become a sort of a responsible state. They were until February 24th of last year. This is Lev Ryabev, who was my counterpart in their Los Alamos years ago. And he actually is responsible for the name of the book, which I show here, and that is that he said we were doomed to cooperate because we arrived in the nuclear century all in the same boat, and a move by any one of us will affect every one of us. And so in the nuclear world, you have to cooperate. You have to cooperate, whether it's India, whether it's Pakistan, whether it's North Korea. That's what we tried to do. Okay, I won't show you most of the rest of these. Let me try to run through these. Actually, this one and then one more. So, Jay, to your question about stockpile stewardship, and plutonium aging is just one of those issues. So it's been 30 years, actually last September 23rd, it's been 30 years since the United States did its last nuclear test, and it was a Los Alamos nuclear test in Nevada. So we've now gone 30 years without nuclear testing. As any engineer will tell you, testing is absolutely crucial to your understanding and the safety, security, and the functioning of what you have. And it's remarkable that we've been able to put it all together and that we still have confidence in the stockpile today. I signed the first two confidence letters to our president in 96 and 97 that without testing we were still able to certify our nuclear weapons. It's still being signed today. Mine were sort of one page long. Today they're 15, 16, 17 pages long because they're more provisos and concerns, and plutonium aging is one of those biggest concerns. So here is my Russian counterpart, the director of the Russian Nuclear Weapons Laboratory, gave me this cartoon, and it captures the spirit of the challenge of nuclear weapons. He said, yesterday, you know, here we were, we had the bombs, we had the computers, we had lasers, we tested, we did it all. Today, this was around 1996-7 time frame, he said, we can only think about the testing part, but we have the old man, lecturing and trying to teach the young one. Tomorrow, when the old man is gone, that young man's going to be there scratching his head because that is such a difficult job. Okay, so. Okay, so with that, I'm going to end on the following note, since we had a lot of discussions about Ukraine and the concern, and I was asked the question, what concerns me today? So this is what concerns me today. So you've had the discussion, could a nuclear weapon be used in Ukraine? I think the probability is low, but it's not zero. And in the nuclear world, not zero is very, very dangerous. So we don't know whether Putin's going to use nuclear weapons or not. However, what I believe is that he's already blown up the global nuclear norm. And there are many who say, what do you mean global nuclear norm? We were never that comfortable with the way the nuclear world was built in the first place. But what I say, look again, from my standpoint, nuclear norm was no nuclear weapon has been used since 1945. Everybody predicted from Oppenheimer to President Kennedy to others, we're going to have dozens of countries with nuclear weapons. We don't. We have less than 10 today. And I say, hey, it's not good, but that's not bad. It's not many dozens. And then third, nuclear terrorism. That's what we worried about 9/11. So my first thoughts after 9/11, suppose that was a nuclear weapon. Or even suppose they put plutonium-238 in that plane. What would happen then? We've had no nuclear terrorism. That is simply remarkable. And then fourth, we've had the good parts of nuclear energy and nuclear medicine. There's some 40 million people either diagnosed or treated with nuclear medicine today. That's pretty good. And it took cooperation. And what Putin did is he blew up all of that cooperation. How can we cooperate with the Russians on nuclear energy? You know, and they've clearly, I mean, they've just destroyed this whole non-proliferation regime that we have, which is this complex scheme of things. So with that, I'm sorry, I will end right there. Thank you.